All right, this next and last section of our chapter here is still going to be talking about exponential and logarithmic equations, but more so like getting into the solving for a variable. You've been spending time kind of being able to like go back and forth between logarithm and exponential form. You've been able to expand logarithms or condense them. What we're going to do now is we're going to actually solve these equations. So there's going to be a variable involved, and we're going to go over a couple of different scenarios that you might run into and kind of how you should approach each one. So the first scenario I'm going to go over is how you would use like bases to solve an exponential equation. Remember, the base would be the number that is being raised to a power. So in this like generic example here, the b would be your bases, and the excuse me, those are raised to those exponents x and 5. If you have like bases like we do here, basically what you can do is eliminate the bases, and then you're left with just the exponents, so the x and the 5, and you just set those equal to each other. Now, this is a pretty like really simple, easy example. Sometimes the exponents might be a little more complicated, and you might have to solve using your algebra skills and like do something a little bit more in depth, okay? The other thing to consider is that you may not be given a problem that has like bases right away. You might actually have to find like bases first before you can actually do any solving. So for this one, it says 25, 3x minus 6 in the exponent is equal to 125. Now, currently, the 25 and the 125 would be your bases, and those are not the same number. So we're not able to just cross them off and then use our exponents. We have to get these bases to look like each other first in order to satisfy this. So a lot of times when we're looking for bases, you're looking for a small number, like a 2, 3, 4, 5, and you're trying to think about raising it to a power to get to the numbers that you started with. So since I started with 25 and I'm starting with 125, I can't probably use just 25. That's probably too big, because if I start to even square 25, it's going to be over 125. So instead, I'm going to try to think about, is there even a way I could rewrite the 25 as a smaller base raised to a power? And can I use that same base for 125? So my thought is to use 5, just because I know 5 can be squared to get 25. And then if I check, 5 to the third is going to get me 125. So if I look here, what they did on this problem is they rewrote these bases as 5 squared. So 25 became this 5 squared piece, and the 125 became 5 to the third power. Now that we have these like bases, we can basically drop the 5s from the problem, and we can work with just the exponents. Now, over on the left side, you have a 2 from when we rewrote the 25, and then the original exponent was 3x minus 6. So how they wrote that down here is they put the 2 out front and the 3x minus 6 in parentheses. We don't want to just stick the 2 onto that and then change that first term to like a 23x. That's not going to mean the same thing. Then they took the 3 from the 5 to the third and they just dropped that down. So now you can see we've gotten rid of those bases. We're now just working with an algebra problem here, and we're trying to solve for x. So what I'm going to do first is distribute the 2. So this says 6x minus 12 equals 3. And then we're just going to keep going with this. So I would add the 12 over to the 3. So I would have 6x equals 15. Then I would divide by 6. That's not going to come out nicely. If you think about 15 over 6, it won't divide to like a whole number, but you could reduce the fraction. So this would become 5 over 2 if you take a 3 out, or you could rewrite it as 2.5. That would be another way that I would accept your answer. So you can either give me the fraction or you can give me the decimal. All right, I would like you guys to try this next one. So I'm going to give you a couple minutes to go ahead and work through that. Okay, let's go over this one here. So the first thing you should have done is you needed to rewrite the 8 and the 4 so that they both had like bases. And how I would have done that is used 2's. So I would have rewritten 8 as 2 to the third power. And then I still have x plus 2 on the outside. Then I would have rewritten the 4 as 2 squared. And then we still have x minus 3 on the outside as well. Now that I have like bases, we can get rid of these. And we can just focus on the exponents. Now this time you're going to have to distribute the 3 on the left and you're going to have to distribute the 2 on the right. So you have to make sure that you do that both times. So when you distribute, it should say 3x plus 6 equals 2x minus 6. And then when you got your like terms together, it should have ended up saying x equals negative 12. All right, let's go on to the next set of problems on the next page. These ones are going to be a little different because it's not possible for us to always get our bases to look the same. Sometimes we have numbers that we can't rewrite and have them match and just drop them off from the problem. So when this happens, we might have to use our ability to switch back and forth between exponential and logarithmic form in order to rewrite it. Remember, that's what you guys would have gone over in like one of your first sections of this chapter, is being able to go like back and forth between log form and exponential form by rewriting the problem. So we're going to do that yet today when we're trying to solve these. So we're going to isolate the exponential expression, and then we're going to either take the common logarithm of both sides, or you could take the natural logarithms on both sides for equations that have bases other than 10. And then you're going to simplify using one of the following properties. Okay, so you can see down here, they're kind of showing you how you could rewrite it with those exponents, also using a little bit of that power rule property where we kind of moved the variable to the very front, or we moved the exponent to the very front of the problem. So we're doing a little bit of that as well. And then we're going to solve for our variable like we were doing on the last couple of problems. All right, so if I take a look at this first example here, I have 5 to the x power is equal to 134. Now I cannot get the 5 and the 134 to match. Like I can't rewrite 134 with a base of 5, which is why I can't handle this problem the same way that I did the last one. So what I'm going to do instead is I'm going to do the logarithm of both sides. So I put log next to the 5 to the x power and log next to the 134. Then I'm going to use my power rule, which says I can take this x and I can move that to the front of the problem. So now it says x times the log of 5 equals the log of 134. Now right now this x is being multiplied to the log of 5. So if I wanted to move that away from the x, I would have to divide. And we can see that happening here. We're dividing the log of 134 by the log of 5. Now at this point, it's just going to be going to your calculator. So you're going to want to grab a calculator here that has the ability to perform logs. And we're just going to type this in. We're going to hit log 134, and we're going to divide that by the log of 5. You're going to get a decimal. Let's go ahead and round it here. Mine says 3.043 and it goes on. So my answer that I wrote down was 3.04. If I were to do the natural log, the same thing would happen as far as my answer goes. So when you're working with this, you can kind of go either with the logarithm or with the natural log. It shouldn't make an impact on your answers at all. So you should just be able to kind of go either direction. So you'll see the first couple examples I work with are going to focus on using the logarithms, and then we'll also show you some examples with the natural logs. Why don't you guys go ahead and try the next example here on your own? Okay, for this one, you could have either done the log of both sides or the natural log of both sides. I'm just going to keep it consistent with that last example and do the log. So I add that onto my problem first. Then I would have moved the x to the front. So this becomes up here. And if you want to put that multiplication sign in there, you can, just so that you remind yourself of what operation you're going to have to do to remove it, which would be division. So I'm going to divide both sides by log 6. So then these are gone, and then over here, it's back to just using your calculator. You're going to do the log of 235 over the log of 6, and again, if you round it like we did the last problem, you get 3.05. Now, like I said, sometimes you can also do these problems with using the natural log instead of using log. So instead of using your LOG button, you might want to just use your LN button. It should not make an impact on your final answer. You should be able to do either one and be able to solve. So if you guys go on to the next page here, I'm going to show you how this works with just the natural log. And the other thing I'm showing you here is on both sides, there are bases that are not alike, but they both have exponents. And so we're going to have to kind of see we move those exponents 2 times. And the other thing that happens here is our exponents are a little more complicated. So this problem is going to take us a little bit longer to work through here. So you can kind of see how they started it is they added in those natural logs in front of the terms. And then what they're going to do is take these exponents and they're going to move them to the front of the problem. And they're going to do that on both sides, just like we were doing on the last problems. So now I have 2x minus 1 times the natural log of 3, and I have x plus 1 times the natural log of 7. What I'm going to actually do here, because my exponents are a little bit more complicated, is I'm going to distribute them to the natural logs that follow. So I'm going to take 2x and distribute that to the natural log of 3, and I'm going to take x and distribute that to the natural log of 7. Okay, so there's my new expression. Now the reason why I do that is because my exponents each have an x involved, and I want to get those terms together. And I want to get my terms that don't have x's, I want to get those together as well. So to do this, I'm going to take these two terms here and I'm going to switch them around. So I'm going to move the natural log of 3 over to the right side, and I'm going to move the x natural log of 7 over to the left side. I just kind of want to do a little switcheroo here. So 2x ln 3, we're now going to have it say minus x ln 7. And then on the other side, it's going to become a positive ln 3 and plus ln 7. Again, the whole reason why I did that is because I want those terms with the x's to be together on the same side so that I can take the x out. So think about what we were doing when we were factoring using our GCF method. We were looking for anything that they had in common that I could take out. In this case, I just want to do the x. So I'm going to pull that out. And that leaves me with my 2 ln 3 minus ln 7, and then the other side stays the same. Now, to get rid of the x, just like we were doing on the last ones, we have to divide. Like on that last example, we had x times the log of a number. We had to divide by that logarithm. We're going to do the same thing here, except you're going to divide by this whole big quantity. You're going to divide it by the 2 ln 3 minus ln 7. You're going to do that on both sides. So these are gone, and now you're going to have to do this math on your calculator. Now, I would be really careful with doing this. It can be really easy to make a mistake. You have to make sure that you're putting in parentheses. You don't want to leave anything open, because if you leave something open without closing the parentheses, it causes issues when you start typing in more stuff, okay? So I would, even if you're like maybe a little too worried about making a mistake, do the numerator first and get your decimal, do your denominator, get a decimal, and then divide those, and then that should get you your final answer. So why don't you guys try to figure that out, use your calculator here, and then we'll see if you guys got the same thing I did. Okay, when you did this, hopefully you got 12.11 if we round it. Again, if you're not getting that, check to see if you close parentheses, or like I said, break it into smaller chunks so that you're not trying to do too much at one time, because that's when mistakes can happen, especially when there's a lot of operations, a lot of natural logs or logarithms involved in the problem. You just want to be a little bit more careful with typing that in. Go ahead and try this next one by yourself. Okay, so what I would have done to get this started is added on the natural logs to both sides. Then I would have moved my exponents to the front. Then I would distribute. And then I would have moved some things around. I would have moved the x ln2 over to the left and the 3 ln5 over to the right. Then you can take out the x from the left-hand side. And then to finish it off here, I'm going to divide by the 2 ln5 minus ln2. And then like before, this is going to be a lot of calculator work. So you just want to type all of that in and it should give you negative 3.83. All right, if we go over here to the next page, I kind of mentioned this before, but there might be times where we can't just get our like bases, or there might be times where we have to do like the log or the natural log of both sides. In this case, one of the sides might already have a log or a natural log built into it, where the other side does not. And so we kind of have to approach these ones also a little bit differently than the other ones, because we can't just We can't add an additional logarithm when something's already got a logarithm on one side. So in this case, we're going to use those properties that we talked about where we're kind of writing exponential and logarithm forms back and forth with each other. Now, when we do these, we will want to be a little bit careful with our answers at the end. We want to make sure that whatever we get for our variable that we solved for, when we plug it back in to the logarithm that we began with, we want to make sure that we don't get a negative number inside of our logarithm. So what that means is if I had something that said like log -4, this is not something that can be done. If I try to type that into my calculator, I'm going to get an error message because it's going to say that it's not a real answer. So it can't perform that. Very similar to like if you try to take the square root of a negative number on your calculator will not do it because it's not a real number. So we can't have things that look like that. Okay. So when we get our answers for these problems, we have to make sure that when we go to plug it back in, that we're not seeing negatives show up inside the parentheses that follow the logarithm. Okay. So when we have these, we might have to start first by rewriting it. If remember, when you have something in log form and you're rewriting it in exponential form, you're just moving some pieces around from the problem. So for example, if I started out with log base 2 of x minus 4 equals 3, this little 2 here, the base of the log, that becomes your big 2 at the front, and this 3 becomes the exponent, and then the x minus 4, that gets thrown after the equal sign now. So we're just kind of rearranging. You've done this before, and now we're going to solve. So 2 to the third power would be 8. We would set that equal to x minus 4. We'd add 4 over, and we would get 12. I need to check my work here, so I'm going to come and take this 12 and imagine what happens if I put it back into this problem. So I put a 12 in for the x. This would say log base 2 of 8 equals 3. That's not going to be a problem because the 8 isn't negative. So this is a good answer. We can go ahead and keep the 12. If I were to plug it back in and let's say I would have gotten a -8, then that would be an issue and I'd have to throw out this answer because it wouldn't be any good for this problem. Okay, you guys try that second one. So we would have started by rewriting it. So it would have been 4 squared equals x plus 5. This would become 16 equals x plus 5. And so we get x equals 11. Again, we would check it. If we put 11 in for the x, this would now say log 4 of 16 equals 2. That's good, so that's an okay answer to keep. Now we can do something similar if there's a natural log in the problem. So instead of it saying log, that's when you're going to see ln show up. So for example, this first one says 4 times the natural log of 3x equals 8. I'm going to divide both sides by 4 to move that over to the other side and get the natural log alone. So that becomes a 2 over here. And then when they go to rewrite this, when you rewrite something with a natural log, that becomes e. You guys also would have learned about e at the beginning of this chapter as well and kind of what that means and what it represents. But so the natural log becomes an e. Again, your 2 becomes your exponent, and then the 3x comes after the equal sign. Now for this one, to get rid of the 3 in front of the x, you'd have to divide both sides. And so on your calculator now, you're going to do this e squared divided by 3. Again, you're going to want to just use your calculator to do this. And you get about 2.46 if we round it. Now again, if I take that and I plug it back in up here, 3 times 2.46 is 7.38. So this would now say the 4 times the natural log of 7.38. That's not a negative number in there, so it should be a good solution. You guys go ahead and try the next one. Okay, so the first thing I would have done on this one is I would have divided both sides by the 6. So it says ln 5x equals 4. Then I would have rewritten this, so the ln becomes an e, 4 becomes the exponent, equals 5x, and then I would have divided both sides by 5, and then I would use my calculator. I would take e to the 4th power, and I would divide that by 5, and I get 10.92 when I round it. Again, if I were to plug that back up there into my x, it would be positive, so I can keep that. Now, if we go to this next one, this will be the last one that we cover here today, and we will finish up the rest of these notes tomorrow. So on this next one, we have 2 terms on the left-hand side that both have logarithms, and then on the right side, it's just a 1. The first thing that I'm going to do with on the left-hand side is because there's 2 logs and they have the same base number. Remember, this log technically has a 10 next to it. When it's just a log by itself, that's technically a base 10. And since it's being added right now, I can combine them by using multiplication. So I rewrote this as log and then x times x minus 3 and then still equals 1. Now on the next step, you can see how they have a 10. Let's talk about how they got to this 10 here. Remember when log is by itself, it has that base of 10. And so this is, being equal. I'm going to kind of ignore this part for right now. This is being equal to 1 if I'm going to rewrite this using my exponential. Well, this would become 10 to the 1st power, which is just 10. Anything to the 1st power is the number itself. So we're kind of just skipping ahead there. We're recognizing that that would just become a 10. And then I also distribute the x here. That's where they're getting the x squared minus 3x from. Now, when I see an x squared, that leads me to start to think that I'm probably going to have to factor this or do something along those lines in order to get 2 possible solutions. So I subtracted the 10 over so that everything's on the same side, and I wanted to keep my x squared term positive, so it says x squared minus 3x minus 10. Then I start thinking about factoring. What are 2 numbers that multiply to negative 10 and add to negative 3? Negative 5 and positive 2 do that. So I wrote it out as x minus 5 and x plus 2. Then in order to solve, you set each of these equal to 0, and we get x equals 5 and x equals negative 2. Now we want to make sure that we go back and check these. So if I plug in a 5, I'm going to do that down here in my check. If I plug in a 5 for my x's, it would say log 5 plus log 5 minus 3 equals 1. This would say log 5 plus log 2 now equals 1. If I were to condense these together, it would become log 10 equals 1. And remember, this technically has that little 10 as the base, so it checks out. This would actually be 1 equals 1, so that makes sense. So 5 is a good answer. We can keep it. Now, for the negative 2, I'm going to do the same thing. I'm going to plug it in. I'm going to get log negative 2 plus log negative 2 minus 3 equals 1. What's going to happen here is this is going to say log of negative 2, and this is going to say log of negative 5. we can't have these negative logarithms. These are causing problems. I'm just going to say this is not good when we're in math. So we can't have a negative logarithm. If you try to evaluate this in your calculator, it's not going to work out. So we have to throw out the -2. It's not a good answer for us. Like I said, this is where we're going to stop for today. We have a couple more problems to go over here in this section, and we're going to do that tomorrow in class together.